Ultrasonic motors represent a paradigm shift in precision engineering, harnessing high-frequency vibrations to achieve motion without the electromagnetic coils or gears that define traditional motors. Operating at ultrasonic frequencies, typically above 20 kHz, these devices convert electrical energy into mechanical movement through the piezoelectric effect, where applied voltage causes ceramic materials to expand and contract rapidly. This generates elliptical or traveling wave motions at the stator surface, which frictionally couple with a rotor or slider to produce continuous rotation or linear displacement. Unlike conventional electromagnetic motors, ultrasonic motors deliver exceptionally high torque at low speeds, near-instantaneous response, and sub-micron positioning accuracy, all in remarkably compact packages. Their silent operation, lack of electromagnetic interference, and ability to hold position without power make them ideal for environments where precision, compactness, and reliability are paramount. As industries demand ever smaller, more accurate actuators, from medical devices to aerospace systems, ultrasonic motors emerge as the future of precision engineering, bridging the gap between macroscopic machinery and nanoscale control. The foundational principle of ultrasonic motors lies in piezoelectricity, discovered in the late 19th century but applied practically to motors only in the 1980s. Early developments, particularly traveling wave ultrasonic motors patented by Japanese researchers, exploited the superposition of two standing waves phase-shifted by 90 degrees to create a propagating elliptical wave on the stator. This wave drives the rotor through frictional contact, with teeth or contact points optimizing force transfer. Standing wave variants, simpler in design, use a single vibration mode to produce intermittent inchworm or impact-driven motion, offering advantages in simplicity and bidirectional control. Both types operate far beyond audible ranges, eliminating noise and vibration issues common in geared systems. Power is supplied via sinusoidal or burst waveforms at resonance frequencies, where amplification of displacement reaches tens of micrometers, sufficient to generate substantial torque despite small amplitudes. This resonant operation yields efficiencies up to 40–50% in optimized designs, competitive with or superior to small electromagnetic motors, especially at low speeds where the latter suffer torque drops. The advantages of ultrasonic motors profoundly distinguish them in precision applications. They provide high holding torque without continuous power input, as static friction locks the rotor in place once voltage ceases, a feature invaluable for camera lenses, robotic joints, and optical instruments. Response times are on the order of milliseconds, enabling rapid start-stop cycles essential for scanning or autofocus systems. Their immunity to magnetic fields suits them for MRI-compatible medical equipment and space environments with radiation or electromagnetic disturbances. Compactness is striking. Motors with diameters under 10 mm deliver torques comparable to much larger electromagnetic counterparts. Wear is minimized through careful material selection and preload control, with some designs achieving millions of cycles. Additionally, they operate across wide temperature ranges when using advanced piezo ceramics, and their backlash-free direct drive eliminates mechanical play, ensuring repeatability down to nanometers. In practical terms, ultrasonic motors excel across diverse fields demanding ultra-precise motion. In consumer electronics, they power autofocus and zoom mechanisms in smartphone cameras and mirrorless systems, where fast, quiet, and accurate lens adjustment is critical. Medical robotics benefits immensely. Miniature ultrasonic motors drive endoscopes, surgical tools, and haptic feedback devices, offering sterilizable, non-magnetic actuation in confined spaces. Aerospace applications include satellite antenna pointing, valve control in propulsion systems, and precise mirror adjustments in telescopes, where weight savings and reliability in vacuum are essential. Industrial automation employs them in semiconductor manufacturing for wafer positioning, atomic force microscopy stages, and pick-and-place robots requiring sub-micron accuracy. Emerging biomedical uses include implantable drug delivery pumps and prosthetics with lifelike motion. Linear ultrasonic motors enable high-speed, high-precision stages in metrology and laser processing, while multi-degree of freedom variants combine rotary and linear motion for complex manipulators. Recent advancements have accelerated the adoption and capabilities of ultrasonic motors, pushing boundaries in miniaturization and performance. Developments in miniature ultrasonic motors, MUSMs, focus on sub-millimeter scales, with stator geometries like cylindrical, disc, or bar shapes enabling integration into micro-robots and endoscopic tools. Bulk piezoelectric materials and advanced fabrication techniques, such as laser micromachining and 3D printing of ceramics, improve uniformity and reduce manufacturing costs. Novel designs incorporate adjustable pre-pressure mechanisms to maintain performance across variable temperatures, critical for automotive or space applications. Dual stator configurations achieve simultaneous linear and rotary motion with single-phase excitation, simplifying control electronics. High-temperature piezoceramics and composite materials extend operational limits beyond 200 degrees Celsius. Traveling wave motors now boast enhanced energy conversion through optimized wave propagation and reduced wear via advanced friction interfaces. Companies have commercialized piezo motors delivering nanometer positioning over long travel ranges in footprints 100 times smaller than traditional stages, with durability improved by factors of 100 through better contact dynamics. The integration of smart features further elevates ultrasonic motors' role in future precision engineering. Sensorless control algorithms estimate position from electrical feedback, reducing hardware complexity. Hybrid systems combine ultrasonic drives with electromagnetic or electrostatic elements for broader speed-torque ranges. In robotics, their high torque density supports lightweight, energy-efficient actuators for humanoid or soft robots. For quantum technologies and nanotechnology, their vibration, isolation, and precision suit cryogenic positioning stages. Market projections indicate robust growth, driven by demand in optics, medical devices, and automation, with compound annual increases reflecting rising adoption. Challenges like wear at high loads and sensitivity to preload variations are being addressed through self-adjusting mechanisms and AI-optimized drive signals. Despite these strengths, ultrasonic motors face hurdles that ongoing research is actively tackling. Contact wear remains a concern in high-duty cycles, though non-contact variants using fluid coupling or magnetic levitation show promise. Driving electronics require precise frequency tracking to maintain resonance amid load or temperature changes, but adaptive controllers mitigate this. Scaling to higher powers while preserving compactness demands better heat dissipation and material advancements. Noise at ultrasonic frequencies, though inaudible, can interfere with sensitive acoustics, prompting damp designs. Fabrication of complex stator shapes and consistent piezoelectric properties pose manufacturing challenges, yet progress in additive manufacturing and doping techniques is resolving these. Looking forward, ultrasonic motors are poised to redefine precision engineering as demands for miniaturization, energy efficiency, and interference-free operation intensify. In an era of micro and nanoscale devices, their ability to deliver macro force outputs from tiny packages positions them as enablers of next-generation technologies. From autonomous surgical robots performing intricate procedures to space telescopes capturing faint exoplanet signals, these motors provide the silent, accurate backbone. As materials science yields tougher piezoelectrics and electronics enable smarter control, efficiencies will climb, sizes shrink further, and applications expand into consumer wearables, environmental sensors, and advanced manufacturing. Ultimately, ultrasonic motors transcend mere actuators. They embody a fusion of acoustics, solid-state physics, and mechanical ingenuity, ushering in an era where precision is not compromised by size, power, or environment.